Good evening, everyone. I'm Dr. Bob Kraus, the Dean of the John D. Odegaard School of Aerospace Sciences, and I'd like to thank you for joining us on this evening and staying later today or wherever you are watching us from. We have a wonderful presentation this evening and a great guest speaker. So I'd like to introduce Mr. Jim Payne. Mr. Payne went to the Air Force Academy, graduated in 1974, learned how to fly gliders there, really took after it. Became a pilot in the Air Force after that, flew a number of aircraft, the F-4, F-5, F-15, F-16, F-16XL. Also went through the test pilot school, did very well there, was a distinguished graduate, but never lost that passion for flying gliders and soaring. And so he continued to do that, earning records along the way. Then, several years later, partway through his career, he went back to the Air Force Academy, became an aeronautical engineering professor, which is where I met him. I was an undergraduate at the time, and he was teaching a flight test techniques course. It was really basically a generic, how do you flight test a Cessna 172, and then how do you develop that into T-38, and it was a wonderful course for me, and it really set me on the course of the career that I had in the Air Force and then led to where I am today. Jim never gave up his passion for soaring and continued to compete to set records, and then he was also a coach of the U.S. International Soaring Team, leading them to 5 different world championships. After he retired from the Air Force, he went to work for NASA and then Northrop Grumman on their Global Hawk program, which we're familiar with in Grand Forks because we have that aircraft out here today. He did that for a number of years, but most recently he's been involved with a project called the Airbus Perlan project, which has been shattering the records that are still in existence today for high altitude sailplane performance, and that's really what we're going to hear about tonight. And so some of the records that he has out there is his fastest soaring flight was 189 miles per hour over a 300 kilometer course. His furthest flight was 1,800 miles in one glider flight. And then his highest flight, which we'll hear about tonight, went up to 76,000 feet in a glider. And so that's one of the pictures that you see on there. You can actually see the curvature of the Earth in that picture. And so with that, I'll turn it over to Jim. We do have a Q&A function enabled, and so we'll try and get to questions if people have them as we go through the briefing. So over to you.
Thanks, Bob. It's been a pleasure here being at the University of North Dakota. Everybody has been so friendly and helpful. So we really appreciate the hospitality. The Perlan project is an innovative group of people that are trying to explore, and we're also trying to inspire people to get involved in aviation and engineering. Our goal is to exceed the altitude record of the SR-71 and do it without an engine, and thus be the highest flying manned wing-borne aircraft in history. So tonight we're going to talk about mountain waves. We're going to talk about building the Perlan 2, some of the logistics of taking it to Argentina where we've done these high flights, talk a little bit about Argentina, something that you want to have on your bucket list, and then talk about flying the Perlan 2. So for those of you that are pilots, in your ground school, I'm sure that the meteorologists have talked about mountain waves. But I'd like to expand on it a little bit, and if you ever have the opportunity to fly out west, or even in the eastern Appalachians, there are some mountain waves. But the mountain waves occur when we have strong winds aloft over a mountain line, and as the air comes over, it kind of descends down the backside of the mountain, and then it rebounds, and you get these waveforms. Underneath the primary wave, there's normally a rotor zone, we call it. This area is extremely turbulent. It's like being inside of a washing machine, and you end up, when you're on tow with the rotor, with full left aileron still rolling right type situation. But in the lifting zone here, you find the most laminar air you can imagine. It's absolutely baby bottom smooth. And the transition from the turbulent to the smooth is the length of a tow rope, which is about 200 feet. And it's kind of interesting. Someplace like Cal City where you're well downwind, take off, you have to climb through the rotor to get to the primary. And you leave the washing machine and all of a sudden you're in this smooth lift and it's rapidly going upwards. I have seen 3,000 feet a minute climbing at low altitude down here. And typically these mountain waves, if there's any moisture at all, will have a lenticular cloud. And they call them, of course, they're lens-shaped. And the one thing unique about these clouds is they're not moving. Even though the winds are very strong, the clouds are forming on the leading edge and dissipating on the trailing edge. On the right here are some lenticulars up high, and then this is the lower level cloud, the rotor cloud. When you do your pre-flight planning, it's always good to look at a satellite picture. If you see a satellite picture, it looks like these. We call these wave bars. Basically, this is the state of Nevada. Where the pointer is Lake Tahoe. And on this particular day, we have a wave field that goes across the state. So the winds in this case are from the left, very strong. And any place you see these wave bars, you're seeing up and down drafts. This is another picture. Lake Tahoe is where the pointer is. Edwards Air Force Base is down here where the pointer is in the south part. And on this particular day, there's an absolutely beautiful wave that is occurring in the Owens Valley. Right here is the town of Bishop. And right in this zone right here, there's probably 3,000 foot a minute climbs available. And there's also a corresponding sink. This is a time-lapse photograph that was taken from a National Weather Service office in Reno looking south. The airport in Reno is on the left, has a north-south runway. So if any of you are ever fortunate enough to be a captain on a 737 going in and out of Reno, if you're climbing out this way, you're kind of in the sink zone from the mountain wave. If you get underneath this cloud, that's where the rotor zone is. And in this edge right along here, you have a very strong, smooth uplift. And when we're doing these long flights in the sailplane, for instance, my 1,800-mile flight, basically we're flying right along the leading edge of these clouds in the rising air. And on a good day, theirs rising so fast we can cruise at redline in our sailplanes. Notice on this particular day that as the day goes along, the moisture increases, so the cloud expands. But if you look at the cloud here, you can see it's forming on the leading edge, dissipating on the trailing edge, and you have a very strong wind that's connecting the 2 points. I was involved in a project at Test Pilot School where we put a pressure suit system in a sailplane. I flew it to 42,200. And one outcome of some of our experiments was that in the lower atmosphere at temperate latitudes like Edwards Air Force Base, the winds are strong up to about the tropopause, and then above the tropopause and in the troposphere, the winds die off. And when that happens, the wave doesn't propagate to high altitude. Well, Einar Voltson was working for Grob Aircraft in Germany, and he saw this graphic that was created by a research vehicle that had a LiDAR that was shining up into the atmosphere over the mountain range between Sweden and Norway. And it shows a graphic of a mountain wave at about 23 kilometers, 76,000 feet or so. And that inspired him to do some research. And he discovered that in the polar regions in the wintertime, there's something called the polar night jet or the polar vortex, which causes the winds to be strong in the stratosphere. And when this occurs, if you have a strong wind in the troposphere that creates a wave down low, that tropospheric wave can perturbate the motion in the stratosphere and cause waves to go to very high altitude. The image on the right shows El Calafate, where we've done our high flights, where this little cross is in southern Argentina. And again, in this case, the winds are going around. The yellow zones there are very strong winds. If you get to the red zone, that's 200 knot winds. When we go to Argentina, we launch weather balloons. We've seen 205 knots at 100,000 feet over El Calafate. So pretty strong winds. Here's kind of a graphic that explains what happens. Again, these only occur in the wintertime at the pole. Of course, in the wintertime, the pole is in darkness all day long. So the air gets extremely cold and it sinks, it starts flowing towards the pole. And because of Coriolis, it generates this strong vortex. The polar vortex is about 40% stronger at the South Pole. I haven't seen a good reason why. I would hypothesize that it's because the South Pole is colder, being a landmass as opposed to an ocean. So Einar got connected with Steve Fawcett, the famous record setter, and they modified a Grob 505 production sailplane. And in 2006, they flew it to 50,722 feet, which was a new world altitude record for sailplanes.
They did that in Argentina?
They did that at El Calafate
Okay.
in Argentina. And on the way down, they decided that they'd do a Perlan 2 project. So the Perlan 2, it's a small team of very dedicated experts, and it's amazing what we've been able to accomplish. During their high flight, they encountered two really significant problems. Number one, a pressure suit starts pressurizing at 35,000 feet. You have 100% oxygen in it, and what that does is it gives you the same partial pressure of oxygen as you would have at sea level. So by the time you get to 50,000 feet, the suit is extremely stiff. So it's very difficult to move. So it's very fatiguing to fly the airplane. Also, the cockpit of the sailplane is pretty small, so it's kind of hard to manipulate the knobs on the dash and so on. Also, if you have a typical canopy, no matter how well you seal it, because of the shrinkage of the fuselage and the canopy, you're going to get air gaps. So the temperature inside the cabin is not much warmer than the outside air temperature. And we've seen with the Perlan at these altitudes, minus 70 degrees C outside. So it can get pretty cold. So Steve, he wanted to build a sailplane that would go to 90,000 feet, be a two-seater, and he wanted to have shirt sleeve environment, i.e. no pressure suit. And the way you do that is you use a safety factor of 3 for the pressurization system in the cabin, which is what they use on space capsules. The aerodynamics are optimized for climb. We have a fixed main wheel because we're at low speed. And oh, by the way, we need to have an aft cabin bulkhead for the pressurization, and you'd have to locate the gear based on the center of gravity, and the two would interfere with each other, so we just left the wheel outside. Airfoil is optimized for flight level 600, which is the altitude at which the rise rate in the air and the sink rate of the airplane, the difference is at a minimum. And true airspeed at high altitude is very high, so you have to really be careful of your design so that you are flutter-free throughout the envelope. This is a graphic that shows the true airspeed. As you go up in altitude, your true airspeed goes up for a given indicated airspeed. If you go to 90,000 feet, your true airspeed is 6.7 times your indicated. Our stall speed is 39 knots indicated. At 90,000 feet, the VNE is 54 knots indicated. So you got this very small region of airspeed that you can use. But if I'm at stall speed, the true airspeed at stall is somewhere around 215 or 220 knots. And if you go out to VNE, you've got a true airspeed somewhere around 370 true. So that's not all bad, because if the wind speed is 200 knots, and I've got these high true airspeeds, that allows me to station keep in the rising air. The airplane is plus 6G to minus 4, flutter-free throughout the envelope. As I mentioned earlier, the pressurization system has a safety factor of 3, so we do not have to wear pressure suits. Okay, the sailplane itself, it's got an 84-foot wingspan. It's a 2,000 pounds max gross weight. It's a two-seater, tandem. We have hatches on the top so the crew can get in and out.
Was the wing and fuselage based on an existing design?
No, the entire sailplane is a complete custom design. Okay. Most sailplanes are designed for cross-country speed. In this case, we're worried about the minimum sink rate. So it has a much larger wing, given the wingspan, or a lower aspect ratio than you'd want on a racing sailplane. Typically, on a racing sailplane, they put the horizontal tail on the top, so you have a T-tail. Main reason for that is if you land off field in stubble that's 18 inches higher, so the tail doesn't catch in the weeds. But in our case, you want a lower tail because that reduces the strength you need to avoid flutter. Just good for flutter. One thing we discovered early in our testing at these high altitudes is you need to heat a lot of things in order to keep them working. So things like the regulators on our air bottle and our oxygen bottle are heated. Tilt camera is heated. Battery even is heated. It takes a little bit of battery power to heat the battery.
It's like
but
you need a battery.
back.
You need a battery to heat that battery.
Exactly. But it turns out that the energy used to heat it reduces the energy loss enough that you actually come out ahead by using some energy to heat the battery. We have a ballistic recovery chute in the center of the airplane. We figured it'd be nigh impossible to bail out with these hatches. We have a drogue chute in the tail for high-speed descent in case we have some sort of emergency at altitude. The pressurization system is actually rather simple. The cabin is designed to have the lowest leak possible. So we still have a slight leak, but in general, we just have a scuba tank which adds air to the cabin to keep the pressure at the level that we want. The cabin, therefore, has 21% oxygen in it. Early on, we occasionally have an oxygen leak, and we didn't want to have an Apollo 1 situation, so we kind of limit ourselves to 26% oxygen. And every once in a while, we've had to vent to get the oxygen concentration down. It's pressurized to 16,500 feet. It can go up to 8.5 differential. And so below 16,000, we just have about 1 psi above outside. And then as we get to this equivalent of 16,500, we keep it at that pressure as we go up. We're using a rebreather system. And this does several things for us. Number one, the rebreathers maybe uses about 1/4 of the oxygen of a normal system. And it traps all the oxygen in the breathing loop so you don't increase the concentration in the cabin. And it keeps the moisture from your breath in the cabin. One of the problems you have is frost on the inside of the cabin. And by reducing that amount of moisture, it makes it easier for us.
So each pilot has their own system?
Each pilot has his own system. And the system includes a carbon dioxide scrubber. That's really the heart of the system that allows it to work. We did test our emergency descent chute. Although we did it reefed, if the chute deployed and then it wouldn't jettison, it's got too much drag to land. So we reefed it, and it worked great and went jettisoned properly. The BRS, of course, you're not going to test that. But we did do one ground test to make sure that the rocket would work and that it would leave the airplane okay. But we do have the BRS.
So once it deploys, then does it, like the Cirrus, does your sailplane go flat, or does it? The picture you had was like straight from the tail.
The folks at BRS convinced us that this is the best attitude for a vehicle like ours. What happens is if you're flat and you've got such a large wingspan, they said it would start oscillating like this. Oh. And you cannot control the impact. Unfortunately, the front pilot's probably going to have some leg injuries this way, but it's more survivable, more predictable. And if you're coming down this way, you can steer it a little bit. If you have some aileron, you can kind of help vector it around a little bit. Before any airplane like this flies, engineers do a lot of ground testing. For instance, we did a wing proof load test. And there's even a lot of engineering involved there. For instance, we had to build this structure because as you load the wings, being carbon fiber, they're going to flex. And the engineers got it right so that the wingtips didn't touch before we got our desired load on.
And so that wing is upside down, correct?
The wing is upside down,
okay,
because we're loading it in a positive direction, yes. Ground vibration test, again, because we're worried about flutter, we did an extensive ground vibration test. We had like 126 accelerometers spread around the airplane. And the engineers, they just have this little vibrator on the wingtip. And the input is so small you can't really see it, but all the accelerometers are putting out data. And from the ground vibration data, from this ground vibration test, they created a model of the airplane. And from the model, they predict the flutter speeds and flutter modes as you go up in altitude. Mm-hmm. And what we do during flight test is we build up, we use 5,000 foot increments and maybe 20 knot speed increments. And we build up from low altitude to higher altitudes and faster speeds. At each point, we compare the test results with the model. If the two agree, then you can be confident that your model is probably accurate and you can proceed to the next point. If the two don't agree, then you have to scratch your head and figure out whether the model is wrong or whether you have some defect in your airplane that might cause it to have a flutter problem.
So is it a molded wing or is it a laid up wing, like a layer at a time?
The wing was built in a mold, so we got a top half and a bottom half and a spar, and then the two halves are glued together. So each half is laid up.
Okay.
Now it's built with pre-preg, and it was cooked, I guess 250 degrees or so.
Okay. And were you concerned at all with wing twist as you deflect an aileron, or?
Wing twist is also a concern.
Okay.
And in our flutter excitation system, we actually have the ability to excite in bending and torsion. But our chief engineer, Morgan Sandercock, he created this system. These little masses are run by stepper motors. They fit inside the spar for the wingtip. The outer 6 feet or so of the wingtip comes off so that it'll fit in our trailer, which was built to fit inside a 40-foot container so we could ship it. And this has been a huge success for us. He can swing these from 2 to 30 hertz, and we got this little display here in the cockpit that's actually doing a transformation on the data and giving us feedback on the response from the inputs from these exciters. And these would turn red if the damping of the particular surface was not good. We've never seen anything go red on us, so that's fantastic. So flying the Perlan 2, we made first flight from Redmond, Oregon in September of 2015. Since then, we've made 4 trips to Argentina to make high flights. We did not go last year because of the COVID restrictions. And unfortunately, Argentina still has a huge COVID problem, and shipping is discombobulated as well as air transportation. So we decided not to go this year, so our next possible campaign would be in 2022. So how do we get our airplane to Argentina? So we acquired a shipping container, a standard 40-foot shipping container. We have a Cobra trailer, which was built to fit inside the container. And then the wings and fuselage were designed so they'd go inside the trailer. Now, unfortunately, in Argentina, it's very difficult to get spare parts. So we also have modified the container on the interior so that we can package it with all kinds of ground support equipment and spare parts. So
Now, did you also bring oxygen and that, or do you got all that stuff down there?
We're able to get oxygen and helium and nitrogen in Argentina. But most other things, you know, like say even a spare tire is difficult to find. So we basically load our supplies in the container, load the trailer in the container, and then it goes by truck from our home at Minden, Nevada, south of Carson City. And it goes down to normally Long Beach near Los Angeles. And then it goes on a slow boat to someplace probably in Mexico, and then it might get transshipped to someplace like Colombia. Each trip seems to be different. And then it, excuse me, ends up at Valparaiso in Chile, which is a port near Santiago. And from there, it goes on a truck through the Andes to Mendoza, Argentina, which is what they call a dry port. And then we make them take it on paved roads down to El Calafate, which is in southern Argentina. There actually is Route 40, which goes along the Andes, but there's segments of that that are still dirt. And we don't want them damaging our glider by running it down a washboard. So when it gets to Argentina, 10,000 miles later, we crane it off of the truck. And in the right picture here, you can see how the trailer opens up. It's a clamshell. And you just roll the fuselage out on a little dolly in the center. And then each wing is laid alongside the dolly.
How heavy is each wing? Is that a 2-person?
We have a mechanical rigger, we call it. Each wing is about 370 pounds.
Okay.
Yeah. So it's a rather beefy sailplane. This is El Calafate, the airport we fly from. The town of El Calafate is 20 kilometers or so from the airport. And it's become a significant tourist town because of the glaciers which are in the Andes. As you go south, the Andes become shorter. The highest peaks in here are around 11,000 feet. And this is about 40 kilometers downwind of the mountains. So on a typical wave day, the winds are out of the west. We take off and just climb straight into the wind. And excuse me, release when we get to the lifting zones. This is a map. So El Calafate is here along Lago Argentino. Lago Vidama is the next lake up. And there is a huge glacier national park that's shared by Chile and Argentina along the Andes here. Absolutely spectacular country. One of the attractions is Pedro Moreno Glacier, which is directly west of El Calafate. And it's a pretty spectacular feature. Here's a photo we took from the Perlan one day. And this glacier starts way back here. It's about 19 miles long. It's 3 miles wide at its widest. On its face right here, it's about 200 feet above the water. One thing that's unique is it crosses this arm of Lago Argentino. And this side becomes dammed. And the water level gets to be 75 to 90 feet higher than on the main lake side. And when it gets to be that high, after 2 to 4 years, it will breach the glacier. So you have a mini tsunami on the other side. It drains down so both sides are level, and then it just keeps repeating its process. But this is one of the glaciers in the world that actually is growing a little bit each year. Pretty spectacular. If you go to the park, they have a really nice viewing area. And again, this is 70 meters, 210 feet or so tall. The glacier moves about 7 feet per day. So if you hang out there...
Wow. I'm videoing. I'm videoing.
You see things like that. I was there with my wife, and she said, "That's going to fall down." I go, "No, darling." And she got a picture of it, so she won. Also in the area is Mount Fitzroy, which is about 11,000 feet. This is a picture of Mount Fitzroy. If you recognize the shape, that's kind of the symbol for the Patagonia clothing line. And this is Cerro Torre, which is one of the 10 most difficult peaks in the world to climb. Interesting part about it is it has an ice cap on top. So you want to get to the peak, you have to take up your crampons and stuff and your ropes and climb around. And I would think it'd be pretty dangerous. It'd be my luck. I'd get on the ice and the ice would break and then be straight down. So,
Did you meet, while you were down there, did you meet people climbing?
you see people climbing.
Okay.
Yes. And they also have some very interesting animals. We're especially interested in birds as glider pilots. And if you go to places like El Chalten, which is near, you see lots of condors. One day I think we counted 22 condors, fantastic soaring birds.
And so those wingspans, they're like 8 feet, 10 feet?
Roughly 10 feet,
Yeah.
3 meters. And one of our pilots actually took this picture at the glacier. And here's a couple pictures of flamingos. Growing up as a kid, I thought flamingos were only in Florida. But you see them in Argentina in the wintertime. So that they kind of wait around and keep the holes in the ice so that I guess they can feed. So flying to Perlan 2, I've got a short video here that our friends at Airbus created for us, showing a flight from El Calafate. So the Aero Club there has been fantastic. Their hangar is big enough for us to put this sailplane inside. Crawl in through the top, through the hatch. The opening is slightly oblong, so the hatch goes in sideways. We turn it 90 degrees, and that way the pressure of the cabin actually pushes the hatch towards the seal and helps keep it sealed. Okay, we're towing with Egret Grove 520, fantastic tow plane. We've made tows to 47,000 feet with it. And typical climb rate is 1,100 to 1,200 feet per minute while we're climbing. So here's a release. This was probably 40,000 feet or so.
So I assume you have different airspace rules in Argentina than you do here in North Dakota.
Yes. Well, they gave us a NOTAM, and so we have a clearance when we fly. And yeah, we're authorized to go to flight level 910. That was fun reporting flight level 750. And coming back to land at El Calafate.
Do you have airliners call you up and say, what are you guys doing up there?
We haven't, but well, we've had them ask air traffic control when we give position reports. In southern Argentina, they do not have air traffic control radar. So they do everything with procedures. Now the Chileans have radar, so they can see us, so we have a squawk. But they do everything by procedure, so you have to give a position report every half hour normally. So this is a picture of the tow plane. Again, we've towed up to 47,000 feet with it, and it's been excellent for getting us into the waves. And here's what it looks like from the sailplane. And we have a tail camera on the egret so we can look at the sailplane. And in this case, just released. See the rope snapped there? We actually had ice on the rope that day. We shed a little bit of ice. So this is a typical flight path. We take off from El Calafate. On this particular day, this is our high altitude flight. We towed to the southwest based on a forecast. We didn't see any lift that we would want to fly in. So we tried more towards the west-northwest and found lift here in the line here, and we just zigzagged back and forth. Now you see we kind of left the lifting zone a couple times. We're doing test points when we're trying to stay in an altitude band, and the lift actually was strong enough that we had to get out of the lifting zone in order to stay in our test band.
What altitude did you release at?
On this particular flight, it was about 42,000 feet. And the high point was flight level 761. The FAI uses GPS altitude now for glider records above 15,000 meters, which is 49,000 feet. So the GPS altitude was less than the pressure altitude. This is a graphic of our altitude versus time. So we released here, and we're doing flutter test points on the way up. So each one of these lines represents a flutter test point. And we did some higher speed test points on the way down. So we're expanding the envelope at higher speed. This is what it looks like from inside the cabin. Remember that we're in the southern hemisphere in the wintertime, and the winds are out of the west. So we spend most of the time pointed towards the west, which means that the right side of the sailplane is in the sun, and it's quite a bit warmer than the other side. I've got a plenum in the window here, and behind the plenum, the window is frost-free. On the downside window where we have shadow, the window, it's almost impossible to keep frost off of it. We got a movie map display, which is a commercial glider flight computer, which was modified for our operation. It's a high altitude flight recorder. We got a tablet display here so they can see the tail camera, although I don't have it up right there. This system right here is our life support systems display. We've got 22 Arduinos spread throughout the sailplane, and these Arduinos gather data which goes on a data bus, and this is probably the most instrumented sailplane in history. We have a telemetry system that transmits the bus data to the ground, so the folks on the ground can observe what's going on in the sailplane, and they're essentially a third pilot because it's easier for them. They got bigger screens and stuff to see some of the temperatures and pressures and other bits of information that are in the airplane.
Do you have any solar panels on this one?
No solar panels.
Okay.
For a couple of reasons. Number one, because it's wintertime and we're 50 south the sun is pretty low on the horizon, so you wouldn't get a lot of energy from the solar panels.
So being that far south, so knowing how far north we are here, how much daylight do you have?
Well, when we first get to El Calafate, it's normally late July, and you get like 8 hours.
Okay.
And by the time we leave, it's towards the equinox, so you get 12 hours. So each week the days get significantly longer. But so this picture here is video taken from the tail camera at flight level 760. And what you see out the window is what you see in the images here. You know, the sky is getting dark, and you can see the horizon has a little bit of a kink in it as it curves. And this is a video taken from the rear cockpit. Again, you can see the tail camera. We actually got a 360-degree tail camera, so you can slew it around you and look behind you and look underneath you, which, given our limited visibility, is an excellent tool because we're concerned about clouds a lot. We don't want to get trapped on top. Although we have instruments to descend through the clouds, we really don't want to because of icing. The down sun window here, kind of frosted over, looking out through the hatch. You can see through the hatch. And this is the right side window, which is frost-free, mainly due to the sun. And if you remember Mount Fitzroy sticks out of the clouds right about there. So a long ways away. In addition to just proving that the waves are there and flying to the high altitudes, we're trying to gather scientific data as much as we can. We have the capability of carrying up to 3 CubeSats, which are little experiments that universities or even grade schools have built. And we had some interesting ones of those.
So they're standard 10-centimeter cube?
10-centimeter cubes,
Okay.
yes. And we've taken some, I guess they call them 2U CubeSats, where there's 2 of them stuck together. But we've had experiments that looked at wave locations and strength, the temperatures, radiation, ozone, dust particle collection, and
Do you get the readout from any of that, or it's recorded and someone else looks at it later?
we see some of the temperature data, but everything else is recorded and people look at it later. The ozone, the past couple of years, the ozone has been exactly per the model.
Okay.
In other words, there has not been an ozone hole over El Calafate. Now I'm sure there might be an ozone hole someplace further south, but at that latitude, it's got a good ozone.
It's over on the Australia side.
There you go. One thing of interest, we've seen significant temperature deviations in the same location, or near the same location, between the rising and sinking air. And typically, this blue air here is the rising air. Notice it's colder. And the orange air here is sinking. And then the red line there was the weather balloon that we set up. You know, Airbus has been a great partner for this Perlan project. And they have a fantastic communications team. So they documented like 5 billion page views from our record.
And I would recommend if anyone's looking for some more stories and videos, go to the website because there's some great pictures there.
Yeah, perlanproject.org, and there's some blogs and lots of other stuff here. But so basically, we've made the world's highest piloted subsonic sustained flight by a civil Aerodyne. Aerodyne being a winged airplane. Okay. Okay. Before I take any questions, since I'm in a university setting, I figured I would offer some mentoring here, some life lessons from an old vet. And with my first slide here, I hope I might change everybody's paradigm about taking care of yourself. My daughter went to the University of Southern California, and President Sample, who was then the dean of USC, he gave the kids a talk. And one point he really made a point of was that they should expect to live beyond 100 years. And when they get to be 100 years old, they're going to have the physical condition of a 60-year-old today. And that's really fantastic, being able to enjoy that long of a healthy life. But what it does mean is you need to take better care of yourself now. You know, lots of exercise. If you think about it, you got to walk 30 miles per pound of fat. So, like last year, I walked 713 miles, which is like 24 pounds worth. Now, for those of you that are pilots, do not fear the flight surgeon. You know, I spent 22 years in the Air Force, and you know, a lot of guys, you know, the flight surgeon, he can never give you good news, because if you're on flying status, that's as good as it gets. But you know, the bottom line is, if you catch a condition early, the flight surgeon can fix it. You know, the heart condition or something like that, you know, these days with stents and a lot of other capabilities, he can fix it and get you back on status. And make sure that you find mentors to help you along the way. Take care of your family. You know, if you're going to live to be over 100, you could be married for 80 years. So, as they say, no one on their deathbed ever says, "I wish I'd spent more time at the office." Now, one thing that Mr. Sample or Dr. Sample made a big point of is, he says, if you're going to live that long, you can expect to have 3 careers in your life. And he suggested the first career be one that helps you become financially secure. And you know, if at the end of your first career you've been able to pay off your house and get the kids through college and so on, then you can go on and be an artist or musician or whatever. You know, in my case, I did 22 years in the Air Force, and then I did 10 years at Northrop, and then now I've been involved in the Perlan project. The Perlan project is a volunteer thing, so I'm not getting paid for it. But and I think this is absolutely fantastic news for women, because if you'd like to be a mother, you know, that can be one of your careers, and you can still have a couple other careers and have a fantastic 100 years of life. But remember, life is not fair. You know, in these modern times, we live mostly safe lives. If I look back at, say, my grandmother's life, you know, they didn't have running water, they didn't have electricity, and so on. You know, things have really gotten better. And, you know, as pilots, we've got to realize the laws of physics have no appeal. So if, you know, you make a mistake, you know, my dad, when I was growing up, always told a story. He lost a friend in a P-38 because he's buzzing his girlfriend's house. And the P-38 has high wing loading, and he didn't pull out in time and crashed into the neighbor's house. So, you know, there's no appeal. And choose to be happy. You know, in part, it's our choice. You know, do what you love and love what you do. The most important job is the one you have now. You know, if you're a flight instructor right now, and you'd like to, say, be an airline captain someday, that's a great goal. But, you know, really put your heart and soul into flight instructing. It's one of the most fantastic things you can do, because you're passing on the knowledge and helping other folks enjoy the beauty of flight.
And as your dean, I would say, if you're a student today, be the best student that you can.
Absolutely, because what you want to do is foster a great reputation. You know, if you're in the Air Force, for instance, and you're a second lieutenant flying T-38s, and you do a really good job, you know, that helps you get selected to fly a F-22 or an F-16. You do a really good job there, and that helps you get into test pilot school, and it just snowballs. And the other thing in aviation, you got to be ethical, because if you're not, you know, people can get hurt or worse. And actually, if you're ethical, you have much less stress in your life. So anyway, I envy your youth, but you know, work hard. So with that, entertain some questions. You know, the Perlan Project's got social media contacts as well as our website. And if you're at all interested in high altitude flight or flying sailplanes, in fact, any pilot should put sailplane lessons on his or her bucket list. You know, the sailplane is the most pure form of flying. You don't have to worry about that throttle thingy. And because of the adverse yaw that's generated by the long, thin wings, you end up having to use the rudder. You know, a lot of guys that say get out of pilot training and go into F-16s where you know, it's a really easy airplane to fly. They kind of forget about the rudders after a while. So anyway, and it's pure fun. You know, if you get involved in soaring cross country and you make these long cross country flights, there's a lot of pilot skill involved, and it makes you a much better meteorologist, if you will. You know, sailplane pilots are some of the best micrometeorologists in the world, because they've experienced the weather. You know, the rising air currents, the thermals, the mountain wave, the ridge lift. It's all fantastic. It'll make you a better pilot, and you'll have a lot of fun doing it.
So I'll add the second to the learning to fly a sailplane, because learning to fly a sailplane was actually the first flight training that I went through, similar to Jim at the U.S. Air Force Academy, and then I moved into general aviation after that, and then Air Force pilot training. We do have one question so far. So it has to do with why are you here this week? So so you're doing some different kind of testing, and so can you say anything about what brought you up here?
So what brought us to North Dakota? We have a customer who has a research project that's ongoing. At this point, it's semi-proprietary. If we have good success, it'll become public. But the atmospheric conditions at about 30,000 feet are basically what he's looking for. Mm-hmm. So the temperatures and the pressures and the dew points, and we're gathering some baseline data for some engine emissions.
Wonderful. We have another question. I don't necessarily understand it. It says, have you ever flown through a hydraulic jump? So that's an atmospheric weather question from one of our professors.
Okay, well, first of all, I'll define what a hydraulic jump is. If you've ever seen a spillway below a dam, the water comes down the dam, and then if you have a flat spot, there's an area where the water's going really fast, and then the water slows down and you see the level of the water is higher. That's a hydraulic jump, basically. Mm-hmm. In Argentina, there was a meteorologist, sailplane pilot that we flew around with, and he was really big on hydraulic jumps. And basically in the atmosphere, sometimes there would be waveform clouds in Argentina, which were well downwind of the Andes. And the only way you could explain them being there instead of in the normal location downwind of the Andes would be a hydraulic jump. So basically what you're saying in that case is you have a strong wind speed, and then as it gets out into the pampa, the wind speed slowed down. And because the wind speed slowed down, it would cause a cycle in the air. So
seems like it'd be much harder to forecast that as opposed to fly along the mountain ridge or fly.
Well, actually, some of the models are pretty good because they're forecasting the wind speed. But well, I ask him, well, how strong is the lift there? And he might say 200 or 400 feet a minute. Well, the lift in the mountain wave is more like 1,000 or more. So I can always go faster in the mountain wave than I can in a hydraulic jump. Okay. So I guess the short answer is I think I've flown in hydraulic jumps. To the sailplane pilot, a hydraulic jump and a mountain wave behave the same. Okay. Except the hydraulic jump might be weaker.
There's another one on there. Because you've been up at high altitude for periods of time, for durations of period of time, are you worried about radiation, and are you doing any radiation measuring?
We have dosimeters that we wear, and we've gathered data. The doses are no worse than some airline captain that's on a 12-hour flight from Sydney to LA or whatever.
Okay. Another person
and of course we got, the cabin is a carbon fiber, so that does provide a little bit of protection, but basically because our durations are small, the flight to 76,000 feet was a little over 5 hours.
Okay. Is there any de-icing or anti-icing equipment on the glider?
No.
Okay.
So, and although we have a horizon, so we could fly in a cloud inadvertently, because the mass of the glider is pretty low, it'd be easy to overgross it with ice. It's not going to perform very well, and we want to,
All right. Next question is, a student has glider experience from back home, was wondering how the Perlan flew compared to a normal glider, and could any glider pilot be able to get into it and fly it, or is it very specialized in handling qualities?
The Perlan flies very much like, say, a Nimbus 3D, which is a long wingspan, open class sailplane. The roll forces are relatively high, but we'd never make big fast rolls. Pitch forces are pretty similar to a normal glider. The biggest challenge is because of structural concerns. The windows are relatively small, and if you have gusty winds, the field of view is such that it's not as easy to see small nuances in the maybe a little bit of the side slip, or if you get a little crosswind, it starts causing you to drift. So it's a little more difficult to see the drift.
So crosswinds, how is the crosswind? How much crosswind can you handle?
We use a 15 knot limit.
Well, that's reasonable.
Yeah. But,
Okay. How long does each flight typically last, and then what's the endurance with the battery?
Our typical Perlan flight, I think we've flown 6 hours and 45 minutes is our longest flight. It was designed for an 8-hour flight, but typically our flights have been around 5 to 5.5 hours. And the battery duration, we've got 150 amp hours of battery. It's really a function of how much heat we have to use. If it's extremely cold, you have to use a little extra heat, then of course that wears the battery down a little bit faster. In terms of my personal flying, my longest flight is 15.6 hours in the sailplane. And as you mentioned, over 1,800 miles for the longest flight.
What kind of sailplane was that?
The 15.6 is a sailplane like the one we have in the hangar.
Okay. Right now, so far, that's all the questions we have. We're still looking for more questions. If not, you guys are going to be here through the weekend. Is that correct?
Yes.
So Saturday, you're going to try and fly again. So we're hoping to see these folks fly again. If you are out at the airport, the sailplane they're currently using and the tow plane are in the maintenance hangar, and it'll be there for the next couple days. And so stop in, take a look at that if you're able to. And then obviously on Saturday, we'll try and get some more flights in. Is there anything else you'd like to add?
No, it's been a great pleasure to be here at UND. As I said, everybody's been absolutely fantastic. So.
All right, well, thank you very much. I'm very proud of being up here too. I've been up here for 2 months. And so we were talking earlier about, what's so great about being up here, and it really is, everyone is so friendly. And so we're glad that we were able to host you and that the folks at the airport have been able to take such good care of you.
So thank you, Bob.
Sure, thank you.